right? Okay, so let's pick it up where we left. So last I saw you guys, we were talking about how we could approximate a function using polynomials. And we talked about how last semester we did it with lines, right? We used the linear approximation, and we spent a bit of time seeing how we could generalize it to parabolas, third-degree equations, fourth-degree polynomials, and so on. And we threw a question right at the end of why stop at, you know, fourth degree, fifth degree, sixth degree? Why not consider all of the polynomials, right? And this ties it up with the question of a series. All right. So and we'll start with one that we're already familiar with. One situation in which we actually could make it work. And this is nothing new. This is something we've seen already. So I'll show it to you in just a moment. So I'm talking about the geometric series. So what was the geometric series? Let's put it closely there. All right, so the geometric series, it looked like this. We had, so I'm gonna make it easier. So I'm gonna make it with a equals 1. So in that way, it looks like this. It looks like r to the k from 0 to infinity. You may remember that one. And we saw that this guy over here had the following behavior. It was convergent if the absolute value of r is less than 1, and divergent else. Right? Now, the interesting thing, though, is that for this particular series, we actually know what the value is. We know what answer we get when it is convergent. So when the absolute value of r is less than 1, we actually know that this expression is actually equal to 1 over 1 minus r. All right? So now imagine that we change this, this letter r, and we make it our usual variable x. Okay, so I'm just gonna write the same thing, but it's I'm gonna replace the letter r with a letter x. So it's gonna look like this. So using r equals x as a variable, then what we get is this. All right, and this captures the idea of what we were trying to do. What we're saying here is that this function, the function 1 over 1 minus x, at least when x, the absolute value of x is less than 1, we can represent it as this series, right? Now, notice the difference in this series. The difference in this series is that this series, it's different depending on what value of x you use. So it's like a series that has a variable. And we're gonna call this power series. So this one over here is our first example of a power series. All right, so well, I'll tell you in just a moment what is the general definition of a power series. But the important thing here is that, like I was telling you, you get a different series depending on what value you input. For example, if x is 1/2 and you put it in there, then what we get is that 1/2 to the k from 0 to infinity is 1 over 1 minus 1/2, right? So that's 1 over 1/2. So that series converges and converges to 2. But this quantity over here actually is a series, right? It's the series 1 plus 1/2 plus 1/2 square plus 1/2 to the cube, etc., right? It just continues over there. But as you can tell, it's not a polynomial like we were doing in section 11.1. It's actually a series. It continues, right? And it makes sense because it converges. So what we're going to be doing in this section 11.2, is trying to figure out if we could do the same thing for other functions. So in other words, we want to see if we can represent other functions, like we did the function 1 over 1 minus x, if we could represent those as power series, or the other way around. If I give you a power series, which I will define in just a moment, can we get a closed form expression for that? Well, is that a function that we know in a different way? And then, of course, the later question is, can we manipulate those expressions? Can we take derivatives? Can we integrate them? Can we use them to do things that we couldn't do before? And we will. So that's going to be a nice thing. So let me show you the definition of a power series. But first, just let me ask you, any questions so far? All right, so let's look at the definition. All right, so see if I could do this, show you directly from the book. All right, so I'm just gonna show you the this is page 722, and this box over here has the definition of a power series. All right, and let's see. So what it says is, as you can see, it's an expression where, let's take a look at this part over here. This is the important part. So it's a series. It has a coefficient, and then it has the part x minus a to the power k. Right, and then these are arbitrary constants, and this is the center. With a, we call the center of the power series, just as we were doing it for the polynomials. If you remember, for the Taylor polynomials, they all had a center. It's the same thing here. A power series is supposed to have a center. And what is very, very nice about power series is that we have this notion of having a convergence in an interval around the number a. So we have the number a. I'll show you a little diagram over here that represents what I'm trying to tell you here. So this is the center right here at a, and there is some interval, this one over here, and for any x that you pick in here, the function will be convergent. The power series will be convergent. And for any value outside, it will be divergent. And it's always an interval centered at A. And how big this interval is, well, actually from the center A to the end of the interval, we call it the radius of convergence. So this distance from A to here is the radius of convergence. All right? So generally that's what can happen. And there are two special cases. One, when the radius of convergence is 0, right? And that means the series only converges for A and diverges elsewhere. And the other is when the radius of convergence is infinity, the entire interval, when it converges for the entire set of real numbers. All right, and we have a theorem that specifies that. Let me show it to you. It's right here in page 723. And it just says again what I just explained to you guys. Let me just put it in, we'll read it together. It says that if we have a power series like this, it converges in 3 ways. Either the radius of convergence is infinity, that's this case over here, in which case convergence is everywhere, from negative infinity to infinity. Or there is some number r, which could be anything. You know, it could be 7, it could be 4, it could be 17, whatever. And then for all the numbers that are within 17 units from the center, it will be convergent. And for those numbers that are further away than 17, it will be divergent, right? Now, notice it says over here, strictly less than and strictly greater than, which brings the question of what happens when it's exactly equal to R. And that's a separate case, and we're gonna talk about it when we look at the examples. And then the third possibility is that the radius of convergence is 0. And in that case, the series, the power series, will only be convergent at the number A. All right? So those are the three possible situations. And we'll take a look at examples of each one of them. And also, to the question of, the important question here is, how do we get this radius of convergence, right? That should be the question that you should be asking yourselves right now, is how do we get that radius of convergence R, right? So we know that inside the interval, it will be convergent. Outside the interval will be divergent. The endpoints, we're not sure. We're gonna learn how to do the endpoints in a separate way. But how do we find this number R? All right, so let's look at some examples, and I'll answer that initial question. How do we find the radius of convergence? So,
Professor, I have a question.
Yes, go ahead.
First, people are trying to join, so I don't know if you need to invite them.
Okay.
My friend texted me, but
thank you. I think I did already.
Yeah.
So
my question, what's the difference between the radius of convergence and the interval of convergence?
Sorry.
Good question. So the radius of convergence is, let me write down actually. So I'll show you a picture, and this will probably clarify your question. So like we said, for a power series, we have our real line, and we have our center somewhere there, A. And we already know that that's the result that I was telling you about, that we have an interval around A. So you go R this way, R to the right, and you go R this way, R to the left. And this, the power series will be convergent here. In the interval of convergence, and it will be divergent out. So if you're out, it will be divergent in all this part over here. All right. So the difference between, to your question, Michael, the difference between the radius of convergence and the interval of convergence is that the interval of convergence is from here to here, all of this, right? It's an interval. And the radius of convergence is a number. It's just, so the radius of convergence, if you want, I can write this. Radius of convergence is exactly 1/2 the length of the interval. All right, does that make sense?
Yeah.
Good. All right. For those of you that just were at it, we pretty much just started. I didn't see that. Next time I will, I didn't see this about the waiting room. So right now there's 30 of you. I think we're pretty much set. We'll iron these little kinks for next time. Maybe I won't have a waiting room. I'll just have everyone added to the meeting right away. But so we haven't done much. We're just starting. We are talking about power series. So power series look like this. They are like series where we have some coefficient x minus a to the k from 0 to infinity. This guy is the center. And these are the coefficients. And then we ask ourselves the question of whether this expression is convergent or divergent. And by a result that we just showed, I mean, we really are not good. We don't have the tools to explain why this will work. Well, actually we do, but we don't have the time really. And it turns out that there's a radius r called the radius of convergence, where the series is convergent here, divergent outside. And in the endpoints right here, I'm gonna write question marks. Right here at the endpoints, we don't know. Sometimes it is convergent, sometimes it is divergent. All things can happen. All right, so we'll do that later on. We'll figure out how to do that. So I was gonna do the first example. So this is example 1. And we're gonna start with part A. And the question is, find the radius of convergence and interval of convergence of each power series. So find radius and interval of convergence. That's what we want to do. And here's problem number 1. Part A is x to the k divided by k factorial from 0 to infinity. All right, so we have this power series, and like I said, it looks a lot like the series we were working with last semester, with one notorious difference. Now we have a variable here, right? This x over here is a variable, so it changes depending on whatever value of x you choose. In fact, this is exactly what we're doing right now. When we try to find the radius of convergence, what we are trying to do is which x's are the ones we can put in here so that this expression makes sense. It's actually a convergent function. All right, so how do we find the interval of convergence and the radius of convergence? That's the question. And the answer is very easy. So the answer to how do we find it is we use, so to find R, we use the ratio test or the root test. You know that there are like cousins, right? When one works, the other one also works as well. But actually, the go-to guy for us is going to be the ratio test, all right? So whenever we want to calculate one of these, we're going to use the ratio test. That's the one you want to use. You will only use the root test when everything is raised to the power k, when there are no factorials, right? Factorials, for example, we cannot really work them out with the root test, but the ratio test will work all the time. Okay, so let's work out this example. Okay, so how do we do it? Well, let's remember the ratio test. For the ratio test, we need to do the quotient of consecutive terms and see what happens to the limit when it goes to infinity. So we need to calculate this limit. L is the limit when k goes to infinity of the absolute value of ak plus 1 over ak, right? And then the only thing you need to remember is that we need to carry around that variable x all over the place. You'll see what I'm talking about here. So here we go, limit when k goes to infinity, and ak plus 1 will be x to the power k plus 1 divided by k plus 1 factorial. All of that divided by x to the k over k factorial. Big absolute value of that, right? And here the absolute value is important because we don't know x. X can be positive, it could be negative, we don't know it, all right? So let's write this down as a single fraction first. So this would be x to the k plus 1 times k factorial divided by x to the k times k plus 1 factorial. And we still have the absolute value bars, right? Okay, next. Next, we simplify it. So what we're going to do is, cancel the x to the k with the power k, so only one x remains, and then simplify the factorials, which I'm gonna do in the next line. So we have 1x that survived, and then we have k factorial. K factorial is 1 times 2 times 3 times 4 all the way to k. And we're dividing by k plus 1 factorial, which is 1 times 2 times 3 times 4 times k plus 1. And just as all the other problems we did with the ratio test and factorials, this simplifies a lot, right? So all of these terms cancel, where only the k plus 1 survives. All right, so let's see what we have. Last expression before we can do the limit is absolute value of x divided by k plus 1. Notice I took away the absolute value from k plus 1 because I know that that number is positive. This number is positive, so there's not an issue there. All right? Okay, so what is this limit? Well, let's see. K becomes big, so k plus 1 will be even bigger, right? And what happens when I divide any number by something really, really, really big? The limit is 0, right? So notice this limit is 0 regardless of x, right? It didn't matter what x equals. It doesn't matter what x equals. The answer to this limit is 0. All right. So then what? Well, then we need to remember about the ratio test, right? How does the ratio test works? Well, we have to compare to 1, right? If the limit is less than 1, it will be convergent. If the limit is greater than 1, it will be divergent. And if the limit is equal to 1, we don't know. It's inconclusive. In this case, it was 0. So the conclusion is that it was convergent. So I know you're not seeing my notebook right now, but I'm going to write it down. So L equals 0 is less than 1, which means it's convergent. The question here is convergent for what values of x? Well, it didn't matter, right? The limit was 0 regardless of x. So that means it's going to be convergent for every x. So convergent for every x. And when it is convergent for every x, then that means the radius of convergence is infinity. So it's convergent for every x. So the radius of convergence is infinity. So R equals infinity. All right. So if the radius of convergence is infinity and it's centered at 0, what is the interval of convergence? Well, the interval of convergence will be from negative infinity to infinity. All right? Okay, so that was the first example. Questions? All right. Good. So let's proceed to, yes, Gerardo.
So the interval of convergence, what is it exactly?
The interval of convergence is the values of x for which the series converges, right? So now we have a power series. In this case, is this power series is x to the k over k factorial, right? And you can use different x's. And the question is, what x's make it convergent? What x's make it divergent? And since the interval of convergence is from negative infinity to infinity, that means all the numbers are convergent.
Okay.
That makes sense?
Yes. Thank you.
Excellent. Let's. This will be better when we see more examples, of course. So let's take a look at example 1, part B. So the question is still the same. find the interval and the radius of convergence and the interval of convergence. But here is our new series. Oh, well, okay. Let me write it down and then I'll ask you a question. So there's something that I didn't tell you about on the previous one, which was the center, right? What was the center on this previous one? Well, it doesn't say anything, right? The expression is supposed to be x minus something. So here the center was 0, right? On the previous one. But on this new one, this time around, our center is not 0. What is our center? Our center for this one is 2. All right. So we have one that looks a bit more complicated. It has this -1 to the k, right? So it's kind of like an alternating power series. But the question is still the same. We need to find out where this is convergent or where it is divergent. And to do it, we're going to use the ratio test again. All right? So let's take a look at the ratio test. How do we do it? Same way. We are calculating a limit L of ak plus 1 over ak in absolute value when k goes to infinity. And what is this limit? Well, let's write it down. So on the top, we have -1 to the k plus 1, x minus 2 to the k plus 1, and in the bottom, 4 to the power k plus 1. And in the bottom, -1 to the k, x minus 2 to the power k, 4 to the k. We simplify this expression. It will be, let's see, -1 to the k plus 1, x minus 2 to the k plus 1, and 4 to the k, divided by -1 to the k, x minus 2 to the k, 4 to the k plus 1, absolute value, right? Now, here we can, first, because of the absolute value, notice that these -1s are gonna go away, right? They're gonna be, the absolute value of -1 is 1, so these guys will go away. And then the 4s are positive, they don't need the absolute value sign. So we'll continue over here. This will be the limit when k goes to infinity. And now we have x minus 2 to the power k plus 1 divided by x minus 2 to the power k, 4 to the k, 4 to the k plus 1. We can now cancel this 4 to the k with the exponent k, with this x minus 2 to the k with the exponent k, and then what survives is the x minus 2 and the 4. And no k's, right? Weird. So we lost the variable k, which makes this limit easy to do, right? It's just a constant. This over here is just a constant. So the answer to this limit is absolute value of x minus 2 divided by 4. All right. Now the question is, same as before, what do we do with this expression? We were doing the ratio test, remember? So we now need to see if this is less than 1 or greater than 1 or possibly equal to 1. And always go for the less than 1 so that you can figure out where is it that, for which values of x is it that this expression is convergent. So less than 1, right? We want to know where this is less than 1. And then now it's going to depend on x, right? It depends on what x's you use. So from here, you should try to simplify this inequality. So from here, we go to x minus 2 less than 4 when we multiply both sides by 4. And that's it. Look at what this is telling you. This is telling you if your number is 4 units away from 2, then it will be convergent. So from here, you know that the radius is 4, right? And let me make a picture. So here's my picture of our situation so far. Oh, by the way, we can, this absolute value inequality, we can rephrase as -4 less than x minus 2 less than 4, which also means that let's say if I add 2, that -2 is less than x less than 6. All right, and this will help with my picture. So here's my picture, my real line. Here's the center. The center is 2. And because the radius is 4, that means I can go 4 units this way or 4 units this way. And so 2 plus 4, that's 6, right? And 2 minus 4, that's -2. So between -2 and 6 is convergent. So all in here, convergent. And we know that if it is greater than 1, if it's on the outside, then it will be divergent. So over here in the outsides, divergent. All right, so we're almost done. There is only the issue of what happens right here when it is -2 or when it is 6. So what about -2 and 6? That's the missing part of what we have, right? So we did x -2. I mean, we know what happens between -2 and 6, and we know what happens when we're outside of -2 and 6. So the question is, what about 2 and -6? All right. So what about? So we did have the problem already. So we know the radius of convergence, but we don't know the interval of convergence yet. So to do that, we need to answer this question, to check 2 and -6. And how do I do that? Well, the way we're going to do it is by plugging these numbers, 2 and -6, into our power series. So here's how we solve this. Plug x equals 2 and x equals -6.
Will it be -2 and +6?
Yes, thank you. My bad. You were right about that. -2 and 6. So that's what we're gonna be doing. We're gonna plug this directly into our original power series, and then we're gonna use our regular tools to figure out if a series is convergent or divergent. Anything you can throw at them that could make it work. Now I can tell you right away, it's not gonna work if we use it's not going to work if we use the ratio test, because these are the points where the ratio test is inconclusive. So don't use the ratio test to check the endpoints. Any other test except the ratio test that you think will be worthwhile. So let's start. Let's start with -2, or with, it doesn't matter. We need to do both of them, so we may as well pick one. So first, let's do x equals -2. All right, so what do we do it? Well, we plug it into the power series. So it will be -2 minus 2 to the power k divided by 4 to the k, from 0 to infinity. All right, let's simplify this. That's -1 to the k. -2 and -2, that's -4 to the k over 4 to the k. All right, now I kind of want to cancel something here, and I can't because of these negative signs. So I'm going to separate this -4. This -4, I can separate it as -1 times 4, right? -1 times 4, everything to the power k. And then I can separate the exponents. So that will be -1 to the k times another -1 to the k, 4 to the k, over 4 to the k. And that's awesome, because now I can cancel these two, right? Now I can also multiply these two now. -1 times -1, everything to the power k. And that's 1 to the k. So look what our power series became. Something super simple, right? It became 1 plus 1 plus 1 plus 1 plus 1 plus 1. What is this? Is it convergent? Is it divergent? Well, divergent, right? Obviously divergent, but if you want to say why, by the divergence test, because the term is not going to 0, right? This number over here should be going to 0 and it's not. Therefore, it is divergent. All right. So we're done. It does not converge at -2. How about 6? Let's check 6. So the same thing, we plug 6 into the original power series. So it will be 6 minus 2 to the k over 4 to the k. And this, when we simplify, is -1 to the k, 4 to the power k over 4 to the power k. This is a bit easier because this obviously cancel. And now all we have is -1 to the k. And we talked about this one before as well. This is like -1 plus 1, -1 plus 1, -1 plus 1, -1 plus 1. And the same thing, the term is not going to 0. So this one diverges by the divergence test. So both of the endpoints were divergent. So then what is the interval of convergence? Let's write it here. Interval of convergence for this problem is going to be from -2 to 6, open on both sides. So these are the x's such that -2 is less than x, less than 6. So strict inequality on both. And if I had to now make a drawing of it, here's my drawing of the interval of convergence. The center was at 2, and we went all the way to 6, not including 6, and from -2, not including -2, or everything in between. So these are open circles, right? -2 and 2 are not included. All right? Good. Questions so far? Okay, let's try the third one, and then we'll do more problems. They're all the same, which is a good thing. So the tool will always be the ratio test. That's a good thing. And then generally, when we check the endpoints, we actually get series that are not that difficult. But let's do example number 3. So this will be part C. All right, part C. This time we're going to do from k equals 1 to infinity, and this is k factorial x to the k. All right. So what is the center? Let's start with that. Well, like I said, we don't see anything here, so the center has to be A. 0, yeah. Very good, Harnit. 0 is the center. Okay, and then the procedure is the same, right? So we take a look at the quotient of 2 consecutive terms when k goes to infinity. So this will be k plus 1 factorial x to the power k plus 1 divided by k factorial x to the k. like that. All right, then we simplify this expression. So right here we can know that we take the x to the k goes away, and this becomes the limit when k goes to infinity of, let's expand the factorial. So we have this k plus 1 factorial, which is 1 times 2 times 3 times k plus 1. Then we have the x. Notice that I removed the absolute value bars outside of these numbers because they're all positive. There's no need. And then we have 1 times 2 times 3 times k on the bottom. These guys all go away except for the k plus 1, right? And now let's see what we have here. We have k plus 1 times absolute value of x. Now, what is this limit? Well, let's see. You may be thinking, well, k plus 1 is going to become huge. And when I multiply something huge by something positive, it will be infinity. It will go to infinity. And you could be right almost all the time. That would be correct, except if x happens to be 0, right? Because if x is 0, then this is 0 times something is 0. And then the limit is 0, right? So this limit has two distinct possibilities. On the one hand is 0 if x is 0. That's kind of clear, right? Because if you plug 0 here, you get 0 times anything is 0. So the limit will be 0. But if x is not 0, then you have some positive number and you're multiplying it by something that becomes bigger and bigger and bigger and bigger and bigger. So this becomes infinity. So it's infinity if x is not equal to 0. All right? So, all right. Now, let's not forget what we were doing. What is it that we were doing? I mean, we were doing this limit, but we often do things like we start doing a limit and we forget why we were doing this limit in the first place. This was part of the ratio test, right? So we want to compare to the number 1. If the limit is less than 1, it will be convergent. If it is greater than 1, it will be divergent. So now we know, right? The limit is 0 when x is 0. So here, if x equals 0, convergent. So if x equals 0, convergent. Else, for all other values, divergent. So this series over here is kind of like a weird series. It's not a very good series in the sense that it only converges when you plug 0. If you plug anything else, it's divergent, right? And when that happens, the radius of convergence is 0. And that means the series only converges in a single point, right? So R is 0, and the radius of convergence, that's the radius of convergence, and I meant the interval of convergence. The interval of convergence is from 0 to 0. Or if you want, just like this, 0, right? The set that only has 0. Or x's such that x is 0. So only 0 works, is what we're trying to say here. All right? Okay, so this is good. We saw 3 examples so far, and we had an example where the radius of convergence was infinity, the entire thing, so convergent everywhere. We have one where the radius of convergence was a number. In this case, it was 4, and we checked the endpoints. In that example, both endpoints were divergent. And we also saw an example where the radius of convergence was just a point, just the center of the interval and nothing else. All right, those are the 3 possibilities that you can get. So it's a good thing that we saw an example of each. All right, so let's do more examples. So now we'll move on to example 2. And let's check example 2. All right, for example 2, Okay, for example 2, we have the following power series from 1 to infinity, and the expression is x minus 2 to the power k root k. Okay, so we already, I hope you have already worked out what is the technique that we should follow. So first identify the center. What is the center here? Good, Daniel, thank you. Center is 2. That's kind of clear, right? Is that not that number right here? And then we do the limit, right? The limit when k goes to infinity of the k plus 1 term over the k term. That's how the ratio test works. And this turns out to be, let's see, is x minus 2 to the power k plus 1 divided by root of k plus 1 times. Now, instead of writing the quotient one over the other, I'm going to flip the one in the bottom. So the one in the bottom, it will be root k and absolute value of x minus 2 to the k. Notice also that I now only placing the absolute value around the things that could be negative. In this case, the x minus 2. The roots don't need absolute value because they are always positive. Okay, from here we can simplify. This goes away with the k exponent here. So this is now just x minus 2. And we can combine these two radicals, the root k and the root k plus 1, into one single radical of k divided by k plus 1. And this will be useful to calculate the limit. All right, next. This is something that I didn't do in the previous examples, but we can do. You know, this limit is with respect to k. K is the quantity that is changing. So for the purposes of this limit, this number x minus 2 is just a constant. And constants, we know we can take them out of the limit. So this we can write as absolute value of x minus 2 times the limit of k over k plus 1. All right. Now, what is this limit over here? This is something we can do. We've done many, many times, right? What is it? See, forget about the radical for a moment. If you forget about the radical, we have k over k plus 1. And we know that when both of them have the same degree, we look at the leading coefficients, right? So this over that will be equal to 1, right? So this limit is the square root of 1. So the answer is then x minus 2 times 1 or x minus 2. All right? And then just as I was telling you, once you calculated this limit, you want to know when this is less than 1. Because when it is less than 1 is that where this will be convergent. So let's take a look at when this is less than 1. Paper. All right, so L is absolute value of x minus 2, and we want to know when this is less than 1. All right, so when is it that this is less than 1? Well, like I said, this already tells you, whenever you figure it out like this, x minus a less than some number, this number over here is r. So this is r. So we're already done with the radius of convergence. The radius of convergence is 1. You can solve the inequality to figure out what would be the endpoints of the interval of convergence. So from here, you can change this to -1 less than x minus 2 less than 1, and then add 2 to both sides. So this will be 1 less than x less than 3. So that's the picture we should have in mind. Here's the center. The center is 2. And we're going 1 unit this way and 1 unit that way. So that's from 1 to 3. And these are the numbers that we don't know. But inside, inside is convergent. These endpoints, we still don't know. Let me put question marks, right? And right now I have them like open circles, but they may be open, they may be closed. All right, so we're halfway there. We already figured out most of it. We only need to check the endpoints. So let's check the endpoints. Check the endpoints. So let's start with 3 this time. Doesn't matter which one you do first. You need to do both. So when x equals 3, when we plug it in the original power series, this is what we get. X is 3, so this will be 3 minus 2 to the power k divided by root k. We simplify it, and what do we get? 3 minus 2 is 1. So it's 1 to the power k divided by root k. So that's just the power series 1 over root k. Okay, then what do we know about that one? Is it convergent? Is it divergent? And why? All right, I see a few of you answering, so good. And both Gerardo and Matt, you are right. So it is divergent, right? This is divergent by P series because the P is 1/2, right? Which is less than 1. All right, so we're done checking that endpoint. That wasn't too hard, right? Let's check the other one. X equals 1. So when x equals 1, now we plug 1 here, so it will be 1 minus 2 to the power k over root k. This becomes negative 1 to the k over root k. Okay, now what about this one? See, it's not absolutely convergent because when you put absolute value bars, this negative 1 becomes 1, and then you get this one, which we already know is divergent. So this one is not absolutely convergent, but maybe it is convergent. And in this case, it actually is convergent. The way we check it is by using, well, the alternating series test. Alternating series test. Why? Because what is the limit of 1 over root k? Well, that's 0, right? 1 over something that becomes really big, it's 0. And also, it is true that 1 over root k plus 1 is always less than 1 over root k because the square root function is increasing, right? This is true because the square root of x is increasing, or 1 over square root of x is decreasing, either way. So once you check these two properties, 1 and 2, from the alternating series test, then we know this one is convergent, right? So convergent. All right, so then to finish off the problem, what is the interval of convergence? Well, we check the endpoints, and for the number 1 was convergent and the number 3 divergent. So we include 1, but we don't include 3, right? So these are the x's such that 1 less than or equal x, strictly less than 3. And if we ask to do a picture, it will be like this. Here's the center 2, and here's 1, and 1 is included, but 3 is not, and everything in between. All right? Questions? All right. Now, something good about power series is that you can combine power series to create other power series. So that's the next little topic that we're gonna talk about right now. So it turns out that if you have a power series, or two of them, and they're both convergent, you can do things like add them, or you can multiply one by a constant, or you can multiply one by the other, and the answer will be another power series that will also be convergent. All right? So let me show you a little bit of that from our book. So how do we combine power series? I'll show it to you. The page in our book, we're talking about page 725, combining power series, right? And right here. So this is what I was telling you about. If we have two power series, say this one with coefficient C's and this one with coefficient D's, you can add them up or do the difference. So if you add them up, you simply add up the coefficients, and if we are in the interval of convergence, that will represent the sum function, the sum f plus g. Or if you did minus, it will be f minus g. So those can work perfectly fine. In the same way, you can take one power series and multiply by x to the m. If you multiply by x to the m, that's easy, right? You can take this x to the m inside of the series, and then by rules of the exponents, you add up the exponents. The new exponent becomes k plus m. And this new power series will be convergent wherever the first one was convergent. And the convergent value 2 will be the function times x to the n. All right? And similarly, you can also do composition. So if you take a function that looks like a constant times x to the m, you can plug this number h into the original power series over here. So instead of plugging x here, you can plug bx to the m right here. And the new function will be convergent, and it will be convergent to the composition function f applied on h of x. All right, I know this is probably a lot to take in. Probably easier if we do a little example. All right, so we'll do one very, very simple one and leave those that are a bit more complicated for tomorrow. Nancy is asking if the question to all of these problems are to find the interval of convergence. And the answer is yes, mostly, right? At least at the beginning. Here, initially, I'm gonna be showing you some power series and then asking you for the interval of convergence. Later on, we'll tackle the opposite problem. We're gonna start with some function that we know and try to find out the power series and then find out what is the interval of convergence of that power series. But for now, yes, the general question to all of these problems is to find the interval of convergence. That's the most general question. All right, so last example of the day. This is example 3. And it says the following. It says, given the geometric series, example 3. So given that we already know this one, 1 over 1 minus x, that's the geometric series, remember? Equals x to the k from 0 to infinity. So this is 1 plus x squared plus x cubed, dot, 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 etc. Keep going, and this formula is true as long as the absolute value of x is less than 1. Given that we know this one, what would be the power series? Find the power series centered at 0 for this function, x to the fifth over 1 minus x. All right, now you see the difference in the question here. So now we already know one power series, which is this one over here. And we're asked to find a new power series or a new function. In this case, this one over here. Now, this is a simple example because you can simply realize that this new one is just x to the fifth times 1 over 1 minus x, correct? So all we need to do is multiply the one we have over here. So this one, we just need to multiply by x to the fifth. So this will be x to the fifth multiplying this one over here. And we can do that by putting the x to the fifth inside. That's what this previous theorem that we had was telling us. And here the roots of the exponents tell me that I can simply write to the exponent k plus 5. And that's it. We're done. If you want so that it looks really like a power series, you can change the index, you know, like we do a J substitution, right? We did this before in class for other things. So you can do k plus 5 equals J. And that way it looks like the ones we have, x to the J. And the only thing you need to figure out is where does J start? And this one started with 0. So when k is 0, J is 0 plus 5. So this one will start at 5, right? You can do this to make it look like a power series. All right. And then the question is, well, what is then the what is the interval of convergence? So what is the interval of convergence of the new one? And the answer next to the little result that we saw is that is the same as the one you used in the first place. So what was the interval of convergence for the original one here? And we can see it over here. This formula works if absolute value of x is less than 1, strictly less than 1. So that means here's 0, and you go from -1 to 1, this one over here. So the answer for our new one is exactly the same. So answer, the same as the original series. That is from -1 to 1. All right. Are there any questions? Someone is asking if these notes will be posted onto Canvas. I'm gonna do it better. I'm gonna post this video of the class we just had here. All right, it will be posted on Canvas, our video of the session. Thanks, Alexandra, for your question. When are you getting the results of your test? As soon as possible. So as you can tell, I have been working on making this, you know, figuring out ways to still teach you high quality classes. So I'm behind on grading your tests, but I will get to them, and eventually I will simply post your scores to our Canvas page. So be patient. All right. Very good, guys. So I'll meet you guys tomorrow the same way. I think I'm gonna not have the waiting room, so I'm just gonna have everyone just join the class as we move along. All right. Stay safe, everyone, and it's good to see you, at least in this virtual way. Bye.